Welcome to SERVOsoft, the optimal solution. This tutorial helps you learn about the supply peak power optimization feature, including its main objective to optimize the supply peak power, as well as the 5 variables used to achieve this objective. Please note that supply peak power optimization is available in the Pro version. The objective is to minimize the supply peak power by finding the best balance of in-feed power and energy storage by adjusting 5 parameters: in-feed supply peak power limit, in-feed region peak power limit, target bus lower voltage, target bus upper voltage, and additional capacitance. In the ideal case, the supply peak power is reduced to a low constant power over the entire cycle. So let's take a look at each parameter. The in-feed peak power limits the supply and region peak power. These values are limited by the in-feed's rated peak power. The target bus voltage values must be within the allowed DC bus voltage range, in this case between 650 and 770 volts DC. You can see this on the main form nominal and threshold bus voltages, and by the tooltip under either voltage input. Increasing the voltage spread between the target lower and upper bus voltages increases the targeted amount of energy that is stored on the DC bus that can be used to feed the application when the supply is limited. This can reduce the on-demand peak power from the main supply. However, a lower VT1 leaves energy storage room on the DC bus to absorb braking energy. This can reduce the region power fed back to the main supply. And recall the formula for energy storage on the DC bus. It is important to note that depending on the application, increasing VT1 may push more energy to regen or braking via a bleeder. But in certain applications, often with low regen requirements, it can be advantageous to have a higher target bus upper voltage. Let's look at 2 sample projects. The first project is a vertical press using a slider crank. The supply peak power optimization feature is targeted specifically for this type of application where most of the energy in the system can be recovered, stored, and reused. In this application, with enough energy storage, it is possible to find the right combination of peak power and target bus voltage values that result in a minimum continuous power. And this is the key: enough bus energy storage. Let's start by looking at the vertical press slider crank project chart. With no supply peak power optimization, the supply peak power is 53 kilowatts. By manually changing the peak power limits and target voltage limits, you can see how I can try and find a solution that works to minimize peak power. These variables can be sensitive, making it difficult to find the ideal combination. But SERVOsoft has a button for that. Clicking on the Optimize Peak Power Start button runs the process that finds the best possible combination of the 4 variables to minimize the supply peak power. In the solution, the supply is limited to 4,338 watts with target voltage limits VT0 is equal to VT1, which is equal to 770 volts DC. Sometimes there are 2 solution types. The first is the lowest Pmax, and the second may have a higher Pmax that is constant over the entire cycle. In this example, there is only one solution, minimum Pmax with constant power over the entire cycle, which is the ideal solution. It is a remarkable result, reducing the supply peak power by 90% from 53 kilowatts to a constant power of only 4.3 kilowatts. This is a common solution in the servo press industry, to use a lot of energy storage combined with managing the in-feed supply power to reduce and smooth out the supply. This project has a lot of capacitance on the DC bus with 487 millifarads. Perhaps this is more than needed. We have over 6,500 joules of unused DC bus energy storage, so maybe we can do a quick scenario analysis and reduce the capacitance and see what happens. At negative 78 millifarads, there is not enough energy storage on the bus. At negative 77 millifarads, there is just enough to maintain a low constant supply power. So how much capacitance do we really need? In total, we need 408 millifarads, but this leaves no margin for any adjustments. So we can probably get away with 450 millifarads. I could then go and select less capacitance to get somewhere near this value. The purpose of the additional capacitance is quick scenario analysis to increase or decrease the DC bus capacitance. Note that C bus can be negative. However, for obvious reasons, the total DC bus capacitance must be greater than or equal to 0 farads. For final design, select products with additional capacitance such that C bus is equal to 0. Now let's take a look at a second project. A 3-axis gantry robot is not a typical application for the supply peak power optimization feature. However, this example demonstrates how to apply the same approach to a range of applications to reduce the peak power, even if it is not able to achieve a low constant supply power. In this 3-axis gantry robot example, the Infeed module rated peak bus power is 30 kilowatts and requires 9 kilowatts of peak power from the mains. The Infeed module has the voltage limits both set to 750 volts DC with 0 joules of energy stored on the DC bus. It's good to note that this is a very peaky application, like most pick-and-place applications are. I will now change the high voltage limit to 900 volts DC, and with the selected 14.5 millifarad capacitor module, the total DC bus capacitance is 15 millifarads with 1901 joules of energy storage. Now I will run the optimization process, and it finds the best solution with the lowest Pmax. The end result is a main supply peak power of 577 watts, a 94% reduction. Next, I will set the number of capacitor modules to 2, increasing the DC bus capacitance to 30 millifarads, providing 3,698 joules of energy storage. Back to the power versus time form. Running the optimization again, the Infeed supply is limited to 345 watts to the bus, resulting in a constant power draw from the mains. Two things worth noting here. First, the supply peak power decreased a drastic 96%, from 9,000 watts to 345 watts. Second, the 345 watts of continuous power represents all the losses in the system. The supply peak power optimization topic is explained in detail in the help file. To load the help page, put the mouse cursor in any of the supply peak power optimization inputs and press F1. It covers everything discussed in this tutorial, including the 4 optimization parameters, PPR, PPS, VT0, and VT1, as well as the 2 sample projects. This concludes the tutorial on supply peak power optimization. Thank you.